Thanks, Derek. Multitasking, I see. Great. I'm just going to wait like another 30 seconds or so. See a couple of people that are kind of joining in as I'm talking right now. I would like to let the folks know that are already in the room. When I do begin the presentation, it kind of hides the chat box and I won't be able to see the questions until the end. The way these webinars are kind of set up is kind of like a one-way line of communication. So I'll just make sure that I go back to the beginning at the end and address anything that you might have. All right, great. So I'm going to go ahead and begin. Hopefully everyone can see my screen okay here. All right, just a quick introduction. My name is Chris Glover. I'm the Director of Energy Recovery Restoration here at Airxchange. It's a fancy way of saying I work with people that have these devices in existing buildings, and I help them either find ways to make them more efficient or replace them when they become inoperable. Today's conversation is going to be on achieving your ventilation goals with energy recovery. First thoughts, I just want to thank everyone for being here. It's going to take about the next half an hour to kind of go through these slides, and at the end I'll kind of cover the questions that you may have on them. Okay, just if you never sat through one of my presentations, what I try to do is create the narrative from multiple different points of view. So depending upon what your function is within the industry, hopefully you'll learn a thing or two. I think for some of you this might be a refresher, or maybe touch upon certain things. But if you can walk away learning one or two things, I think I've done my job and accomplished what I set out to do. So with that being said, let's kind of move along. So a little background information on Airxchange. We were founded over 40 years ago in Rockland, Massachusetts. For those of you who don't know where Rockland is, it's just south of Boston, Massachusetts, and actually quite nice late spring day here. We have over 300,000 wheels in the market, and that's growing rapidly. We are a charter member of the HRI AAERVE committee of HRI. We're a member of the ASHRAE 90.1 mechanical subcommittee. We are a member of the ASHRAE standard 62.1 ventilation committee. We are also a member of the TC55 energy recovery committee. So we are pretty heavily involved in the industry and what it provides in terms of information. We are currently the largest supplier in overall volume to HVAC OEMs in regards to energy recovery products. And all of our products are HRI 1060 performance certified, which I'll discuss a little bit at the tail end of the presentation here. So on the agenda today, we're going to go over a quick overview of the ventilation and the benefit of dilution. We'll address some challenges with ventilation. We'll look at how energy recovery can address those challenges. We'll look at the principal operation of energy recovery devices. And I'll just kind of end with the sources that we use for the presentation and some resources that are available to you. Okay, so let's start off by talking about ventilation and dilution. So let's take a look at a typical ventilation process using outside air. Okay, so outside air goes into the HVAC unit. Now that air may be conditioned, it isn't required to, but it can be. And that ventilation air then gets delivered into the space. The fresh outside air dilutes the stale space air, which is displaced and exhausted outside the building. Kind of a simple process. And the benefit of ventilation is dilution. So dilution in its very basic form is the continual reduction of a concentration of contaminant of concern. I know it's kind of a mouthful, The rate of airflow delivered into the occupied zone is typically presented in cubic feet per minute, or CFM, or sometimes referred to as air changes per hour, which is essentially the rate of airflow delivery as compared to the volume of the space. It essentially refers to how many times per hour the entire volume of air within that space is completely replaced with fresh outside air. So once again, the dilution, there we go. So once again, dilution is the continual reduction of a contaminant source within the with the introduction of fresh outside air. The generalized dilution curve is often used to represent the reduction based on what's considered a normalized airstream. So, and what it shows and what it demonstrates is that every time you double the air changes, you cut the indoor concentration of contaminants in half. Now, the generalized curve is typically used to represent what most folks consider normal kind of occupied space air, not necessarily stemming from a viral or a health-related concern, which kind of everyone is kind of acutely aware of right now. But that's not saying that there isn't a long history of studies that demonstrate the health-related implications as it compares to increasing the amount of outside air into the space. So the science behind the reduced infection rates as it relates to ventilation is often attributed to what's known as the Wells-Riley equation. So back in I believe it was 1955, Wells developed a way to calculate what's known as a quanta of infection, and relate it to an overall infection dose rate. So what Wells did was study an outbreak, I believe it was on tuberculosis, and it's really been used since then to kind of model infection risks as a rate of quanta, which is essentially a unitless dose of infection rate. So it wasn't until 1978 that Riley came along and took that quanta and developed a risk assessment model that established an infection rate reduction with increasing rates of ventilation delivery. And looking at the relationship on the left, it can be demonstrated that the process follows a very similar path to that of the general dilution curve. The Wells-Riley equation has gone through kind of several updates over the years, and it's used to include additional air cleaning technologies like filtration and ultraviolet light, and it's now become known as what's known as the kind of the modified Wells-Riley equation. And this relationship has been used over the course of many studies as kind of a rationale for increasing ventilation rates to manage risk and exposure to potential contaminants. Now, the real reason that I'm kind of explaining all this in so much detail is I want to demonstrate that ventilation, filtration, ultraviolet light, these methods are all additive, and they can all be used to decrease the risk when used in conjunction with one another. And another reason that I'm going to detail is because when you read through these studies, and I'm not going to focus on them, but if you read through them, the associated health gains and cognitive gains are often associated with ventilation rates that would be considered above, what the normalized or standard rate of delivery for that space may be. So leading into that, what determines the ventilation rates we need to use for commercial spaces? So the standard of reference is ASHRAE standard 62.1. It's the ventilation standard for acceptable indoor air quality in commercial buildings. The language that's used in the ventilation standard has been adopted into the International Building and Mechanical Code and is referenced by most states and provinces. I'd like to say that each state does make up their own determination on which to reference, and really what published year is the rate, or excuse me, the standard of reference. Some states even choose to make up their own reference. So it's because of that that the ventilation requirements are going to vary from state to state, and also whether or not the building in question is either in going through a new construction project, whether it's a new building, or if it's an existing building that's going through an alteration or some sort of form of period of repair. I should also state that ASHRAE standard 62.1 is not a health standard. It means that disease transmission was not considered when developing the rates. It strives to provide guidance that provides health, comfort, and occupant acceptability, but once again, it doesn't guarantee it. The ASHRAE Board of Directors has approved a rule stating that ASHRAE standards shall consider these impacts where appropriate, but mostly these rates are based largely on what it takes to dilute normal sources of contaminants inside the space. So now at this point, you might be asking yourself, what is a normal source of contaminants? So, it's largely bioeffluent, coming from the building occupants. Could be odors and potential, things coming from people working in the space, or off-gassing from building materials and furnishings, or any type of a process that might be occurring in the space. And with those elements taken into consideration, it provides the minimum ventilation rates to achieve dilution. So you may notice that at the bottom of that, I highlighted minimum ventilation rates to achieve dilution. And I like to highlight it because as most code-related standards go, the minimum rate often becomes the maximum rate that's used in the space. And if you were to read some of those health studies, sometimes the minimum rates don't provide the best health-related benefit. So there are three, waiting for this to catch up on your end there. There we go. There are three main compliance paths within the standard to determine what the equivalent rates are. So there's the ventilation rate procedure. This is the prescriptive procedure for outdoor air rates, which is based on space type, occupancy, and floor area. You also have the indoor air quality procedure. It's a performative-based procedure where the design parameters are based on an analysis of the contaminants within that space, or the contaminant sources. And then you have the natural ventilation procedure, which is another prescriptive path, but where the outdoor air is being provided through openings into the building from the outdoors. The one that I most commonly see used is the ventilation rate procedure. A sample of that is a chart on the left, and one of the things I kind of want to point out is that not only does it include the metrics needed to provide the ventilation rates, but it also classifies the sources of exhaust air for purposes of recirculation within the building. Now, this becomes particularly important when discussing energy recovery because it basically defines what exhaust sources you can pull air from, and what the maximum recirculation rates from leakage can be when operating them. So we're going through a very interesting time, to say the least. So I think everyone has become kind of acutely aware of ventilation and why it's so important. But if ventilation is so important and provides all these health and cognitive related benefits, why aren't we just dumping tons and tons of outside air into the occupied space? Well, it's really because it takes a lot of energy to condition that air. So if you look at the chart at the left, some of you might not recognize this. This is a psychrometric chart. It's basically a chart that demonstrates the energy properties of non-compressed air. So what I'm trying to demonstrate here is not make you aware of how a psychrometric works, but what the outdoor air conditions. I think it provides a good graphical sense of what the outside air conditions may be occurring. And really what this chart shows you is that within that dotted line, your outside air conditions could be anywhere within that window. So that's a pretty big operational window that you have to deal with. The red and the blue dot represent your typical indoor conditions and both heating and cooling modes. And as you start to move away from those points, the bigger the energy load is going to be on the building. So essentially the hotter it gets, the colder it gets, the more humid it gets, the more energy you're going to have to use to try and condition that air. And it's really because of this big operational window that it really makes it difficult to design a system that can operate efficiently with all those conditions in place. So the true cost of ventilation is usually often attributed to the potential energy savings when you're trying to actively reduce the rates. And it's because of this perception that building owners and operatives usually have a tendency to kind of overestimate the costs associated with ventilation. There was a study that was published by Harvard several years ago, and what I found interesting is they queried the building owners and operators and asked them, what would be the perceived cost if you were to just double the ventilation rates and increase the filtration efficiency of their filters. And largely the response showed that the average person queried said that the increased cost would be about $100 per person per year. It's this perception of cost, this high cost of ventilation, that it often kind of prioritizes and incentivizes the reduction of the ventilation air. However, within that study, they were able to demonstrate that doubling the ventilation rates actually cost less than $40 per person per year across all the Department of Energy's modeled climate zones. Furthermore, the study showed that using an energy recovery technology led to even lower operating costs and even some climate zones at a net savings over a traditional unit operating just merely at the minimum. So looking at that study a bit more, the two systems used in the study, I should say, were a VAV system and a dedicated outside air system. Both modeled a 30% increase in ventilation and a doubling of the ventilation air with and without using energy recovery. What I found interesting is that in certain cases, by using energy recovery, you are actually able to achieve higher ventilation rates at a total lower operating expense. So in these particular cases, you aren't really sacrificing something to prioritize another. The study also demonstrates that with enhanced ventilation rates, the occupants also had better cognitive awareness and better decision-making capabilities, which led to higher productivity, which was usually magnitudes larger than the associated costs for increasing the ventilation air. And the statement really isn't kind of an isolated case to this one study. If you go back through multitudes of studies, there's been a long history of the cognitive benefits of providing enhanced ventilation rates to the space. However, even with those productivity gains, ventilation once again is still often very sacrificed for the energy savings. So the previous study demonstrated that systems. So the previous study demonstrated that systems that utilize energy recovery in certain cases led to an overall net negative operating expense, but it didn't occur in all cases. So in those cases, though, it did increase the operating expense. So that can potentially be perceived as taking away from the profitability of the business, and this matters. Cost savings matters. The chart on the left really kind of demonstrates the typical breakdown of the costs associated with operating a building. And lowering ventilation rates is directly tied to the energy expenses, which is that kind of large yellow expense on the left. However, this chart is missing one key statistic, and that's the cost associated with people's salaries. So adding people's salaries into the chart demonstrates that adding the cost of paying people to do their work is magnitudes larger than that of the energy-related costs. And realistically, people's salaries are the revenue-producing part of the business. So this is something you have to take into consideration. And what my point here is not to try and diminish the importance of reducing energy-related costs, because I think it's a very, very important related task. What I'm trying to demonstrate is that you should be taking into consideration the potential impact on productivity when making some of these operational changes. Especially when you can use energy technologies like energy recovery to achieve enhanced ventilation rates cost effectively, and that cost may be offset by the productivity gains that would occur. Okay, so energy recovery has really kind of been developed to respond to all these challenges that we've been discussing up until this point. The easiest way I can describe how an energy recovery device works is that all it wants to do all year long is bring the outside air as close as it possibly can to the indoor condition. So it does this process passively, meaning as long as there is either a thermal or a moisture-related difference between the air streams, the device is working to perform that work. So, a typical energy recovery system, reduces the energy load associated with the ventilation system by, typically 50–80%. That's kind of what I see being designed on the market. Couldn't you get higher than that? Yeah, absolutely. But once again, you just have to design it for that. So once again, looking at the site chart, what an energy recovery device is really doing for you is really shrinking that operational window from that large dotted line to that solid line. And all that difference between those two windows is your potential energy savings. That's areas where your system no longer has to work in. And this reduced operational window also helps create a more ideal and easier to predict control over the air that'll be coming into the building, make it a little bit easier for you to help maintain certain occupant comfort. So next couple of slides, we're just going to go over quickly how the basics of energy recovery and how it works. So you may remember this slide early in the conversation. We're just taking that same process and adding an energy recovery component into the system. I like to say that the energy recovery kind of acts like a buffer between the outdoor air and the more ideal indoor air conditions. The work that gets provided, I often refer to as a load shift. So in a load shift process, you're essentially shifting the conditioning load of the ventilation air from what would typically be your primary heating and cooling element over to the energy recovery device. The benefit of doing that is the primary conditioning element uses what I consider a high-grade energy source. So it's using either electricity or a gas to condition that air. Whereas an energy recovery component is using what I call low-grade energy, or it's just using low-grade thermodynamic energy. And this is energy that's just normally in the air that you're going to exhaust outside the building anyway. So by cycling this low-grade energy instead of using a high-grade energy, it greatly reduces the amount of energy consumed to treat the same amount of ventilation air for a particular space. All right, so energy recovery is really a fancy name for an air-to-air heat exchanger, which it functions on basic thermodynamic principle. It operates by transferring energy from a high source to a low source. So kind of looking at that example on the left, the outside air is warmer than the indoor air. And as that outside air passes along the heat exchanger surface, I should say, it transfers the heat energy from the outside air to the leaving exhaust air, which essentially cools it down. And now the ventilation air is leaving at a much more ideal condition. Furthermore, energy recovery components can really be divided into two categories. The first being sensible only, so where the process of the component results only in a change of dry bulb temperature. And the second is often referred to as an enthalpy exchanger, where there is a change in both dry bulb temperature and as well as the moisture content of the air. The transfer of this water vapor is referred to as the latent energy transfer, and it really functions in kind of a similar manner, but it is independent of temperature, meaning that it doesn't require a temperature difference. All it requires is a difference in the absolute moisture content of the air, and that transfer is provided through a process called adsorption. Now, this is important because adsorption is the transfer of water vapor in a thin layer of gas. So it doesn't actually physically condense on the surface of the heat exchanger. And this is a big deal because you don't want standing water being on the surface. So all the water transfer is just basically being held in the vapor phase. And when the device goes and rotates into the opposite airstream, it gets deposited and blown out back outside. So once again, looking at the design, as the air moves across the heat exchanger, the water vapor and the heat is going to be transferred from the high humidity, high heat airstream to the dry airstream. So basically what this means is in the summertime, the ventilation air is typically going to be cooled and dehumidified, and in the wintertime, it's going to be heated and humidified. So once again, I mentioned this earlier, energy recovery is a passive process and relies solely on the difference between the state points in order to perform work, which is kind of neat in my opinion. So the amount of work an energy recovery component will provide is normally referred to as effectiveness. The general term for effectiveness is the ratio of the actual work provided over a theoretical maximum. Although the term effectiveness, as it's been used in kind of the industry and out there in the in the commercial market, is kind of used kind of loosely. But for purposes of this conversation, I'm not going to go kind of dive too deep into that. But but in a general sense, what really determines the component's effectiveness is really generally the material and the geometry of the media that makes up the device, as well as the amount of surface area and the velocity of the air moving across that surface area. So one thing that I didn't mention is temperature and humidity. So, and that's because temperature and humidity do not have an effect on the component's effectiveness. So if you have a constant velocity system, the effectiveness is going to remain the same regardless of you have a 2-degree difference or a 100-degree difference. And it's because of this operational characteristic that really kind of allows these devices to work so well, especially in those very extreme conditions that we demonstrated on the slide chart. Okay, so just to quickly summarize some of the benefits of the energy recovery systems, it allows you to maintain or increase your ventilation rate cost effectively. We kind of demonstrated how it does that. Helps manage varying outside conditions. Outside air is tricky. It's I know personally here in Boston, it can be snowing one day and I can be wearing shorts the next, and those are very difficult situations to plan for. It reduces peak energy demand. So as we kind of just saw, the hotter it gets, the colder it gets, the more work these devices actually do for you. The next one's kind of unique to DX systems. So it increases operational efficiency. So, if these devices are equipped on a direct expansion equipment, what you may or may not know is as you start to moisture load a DX coil, you start to lose operational efficiency. So what these devices do is, because they're actively removing heat and humidity from the air, it allows a more ideal condition to enter the evaporator coil, which not only means you're shedding load off the evaporator coil, but also means that you're allowing that evaporator coil to work at a higher operating efficiency. It's kind of a unique operational metric. It allows for better humidity control. As we demonstrated, these devices can transfer from moisture from the humid stream to the drier stream. And as you remove moisture from the air, as it enters the evaporator coil, now it allows that evaporator coil to remove, more moisture than it would have just solely by itself. So you're getting some enhanced humidity control out of it. Some people refer to it as changing the SHR, sensible heat ratio of the system, especially for certain components that have, that get a little less efficient at certain SHRs. Lastly, it allows for downsizing of the primary heating and cooling components. Once again, because you're shifting the load from the primary heating and cooling apparatus, now that you shifted that load over, that apparatus doesn't have to work as hard. You don't have to provide as much conditioning, so you can downsize those to handle just the condition that's required to handle at this point. So you get some benefit from that. Okay, so to complement some of the theoretical information we just discussed, I wanted to show you some real-world data on some some information that I collected on our facility located outside of Boston. So what you're looking at is a chart from the rooftop units that are kind of right above me right now. We have several rooftops with energy recovery components that are delivering kind of enhanced ventilation rates. So we deliver ventilation at a rate that exceeds what the standard rate is going to be, and we monitor remotely some of the performance characteristics with some, what I consider some relatively expensive sensors. So what you're seeing here is what I would consider a typical summer week for us up here in the Northeast. You can see we have a 25-degree temperature swing from day to night. So temperature's on that left-hand axis. And what the graph is monitoring is the amount of work the unit is doing compared to the power consumed, which results in a metric that's BTU per watt hour. So for some of those who aren't aware, BTU per watt hour is a metric is a rate that's used to rate the efficiency of rooftop DX equipment. It's also the unit for what people call EER, which is the how they rate the HRI ratings for rooftop DX equipment. So this particular rooftop has an HRI rating of 12 EER, and what the chart is demonstrating is that on a typical week, the majority of these times, these units, they were achieving higher operating efficiency while using energy recovery at enhanced ventilation rate than what the rooftop would have been able to accomplish completely by itself. To complement that, this is what's considered a design point day in Boston. 95 may not be hot for some of you out there, but it's pretty hot for us. But once again, because the nature of these devices, as the conditions become more extreme, the more work you're actually going to get out of them. So on this very hot day, the system achieved a great operating efficiency without sacrificing the ventilation to the space. So it's typically days like these that most building operators would start to consider scaling back some of their ventilation rates. But in this particular case, you don't have to, because now you shifted that load over to the energy recovery wheel, who's doing all the conditioning for you at that point. So it's kind of a real world scenario here. Energy recovery is an HRI certified technology. HRI 1060 is the performance certification standard. That data that's recorded is public view for for consumption at the HRI directory website. And as certification programs go, it's a fairly rigorous program. To be part of the program, 20% of your basic model groups have to be measured and verified, all of which are chosen randomly and blindly, and all have to conform to the standard. The test itself includes multiple points of test, both with static and variable state points, for really kind of certifying and for the purpose of defining an operating range for these devices. Now, kind of going through this, you might be asking yourself, why is this certified technology important? And I know for us and for some of you out there, it's important because it's a quality control item. You have to be aware of how these devices are going to operate and kind of reliably and accurately predict the performance that they're going to provide you. So I want to talk briefly about the Airxchange product and how its design can help you achieve your ventilation goals. Airxchange offers a full range of energy recovery components. Starting with our synthetic energy recovery wheels, we offer aluminum energy recovery wheels. We have a choice of desiccants, as well as an enthalpic energy recovery plate, all of which are HRA certified. So we certify our entire product line. Airxchange started manufacturing over 4 years ago with the segmented polymer design, and that design was really was introduced to answer the maintenance issues that the older monolithic metal wheels were experiencing at that point. The design allowed us to really kind of introduce this new component that was not only lightweight and durable, but had really good thermal transfer characteristics. As a side note to that, also provide flexibility on how you can design and operate these devices, because the interchangeable segment design allows you to vary the performance characteristics of these devices through a standardized design. Lastly, the synthetic material also allows us to permanently embed the desiccant into the material, which gives end users the ability to effectively maintain and wash these devices according to their resources and based upon the demands of the environment that they're put in. So reliability, maintainability is really part of our business culture here at Airxchange. And we really want these devices to spin for a very long time. And because of that, we place a tremendous amount of time and resources into ensuring that the designs are meet our high standards. Part of that process is ensuring each design goes through an FEA to identify any potential areas of concerns, as well as a life cycle test before it's even brought to market. And in regards to that reliability, the proof is somewhere in the pudding here. So, if you were to analyze our warranty data, we have our standard warranty is 5 years from date of install, you see that the design has an exceptionally low failure rate. So we experience very low failure rates within that period, and it's because of all the time and effort that we put into making sure these products are reliable and maintainable. And really, the reason we put all the time and effort in this design is because we want you to take advantage of these features. In a post-COVID environment, maintaining and achieving good ventilation is going to be imperative. And as the HVAC unit operates, the performance is going to start to degrade, as well as potential airflow delivery, if and when that component becomes dirty. So the cleanable, washable designs gives gives you peace of mind, and the building operator is a cost-effective way to maintain the performance, not only from a performance perspective, but also in maximizing the delivery of ventilation air to the space. I've kind of been speaking in terms of flexibility. There's been a lot of discussion in regards to building resiliency, which to me means being able to operate effectively in future periods of crisis in terms of HVAC system design and operation. So in my interpretation of resiliency in regards to energy cover ventilation is being able to maximize airflow delivery to space without losing control of occupant comfort. So this could mean that sizing the HVAC unit for periods of operation where the outside air would be above the minimum requirements for a certain amount of time, or maybe you're replacing existing components with new components that may achieve that goal a little bit easier. I mentioned this briefly before, but one of the unique features of Airxchange is our interchangeable segment design. And what it does, it allows designers and operators to kind of acutely tailor the performance of the device to their specific need. So the different media options have all been optimized for either high thermal and latent performance, high airflow and low pressure drop, or a combination of both. This variability in operating characteristic gives designers more control over what's going to be best for their design. And if you're in a building equipped with the Airxchange wheel, it allows building operators some flexibility in the operation. As you move from the EFX segments to the PDX segments, it allows you to either move more air across the heat exchanger surface, perhaps maybe to accomplish some more dilution, or maybe to lower the pressure drop so that you can compensate for some higher filtration, or perhaps maybe a combination of both. So kind of looking at the left there, if you're normally operating with a high efficiency segment, if you were to move into the other segments with a lower pressure drop, you may be able to move more outside air into the occupied zone, or perhaps increase filtration. And as you can see from the chart, the transition from a MERV 8 to a MERV 13 is roughly the same increase as the decrease you're getting from a segment swap. So possibilities, flexibility is there in terms of design and operation. So I understand that each case is going to be different, but really it's what's most important to you. And we have the resources and the products available so that you can make those important decisions. All right, so hopefully you learned a little bit during the time here. So I just like to kind of point out some of the sources that I use for this presentation. Send me an email afterwards. I'll be happy to kind of give you this list so you can do some research for yourself. I highly suggest checking out our website at airxchange.com. We have loads of resources that are available for you to kind of help you navigate this environment and determine what's the best what's the best way forward. We also have access to our performance modeling software. So airxweb.com is where we house that. It's available for everyone, so all you have to do is sign up for it on airxweb.com, and it'll give you access to all our model configurations as well as to the certified data that's available for them, and it allows you to quickly and easily and accurately predict the performance of these devices. All right, so thank you so much for staying with me through all that. Once again, I hope you learned a little bit. I appreciate you taking your time on your day to be here. I'm going to switch over to the other screens to see if there's been any questions. But once again, thank you so much. I appreciate you listening in. Okay, so I'm going to go to Okay, so the first question is I work for a utility company that gives rebates. Ours are based on Scfm and other parameters. If there are two wheels in a box, how do we get accurate Scfm from HRI? Does HRI test the Scfm with two wheels, or do we simply double the one wheel design? And if so, is this accurate way to get the effectiveness, since some are set up to run in parallel and some are set up and run in series? HRI only models a single wheel performance. So there is no metric within the 1060 program to model two wheels either side by side or in series. So you'd have to use the HRI data that's available for the singular wheel in a manner that accurately predicts the performance for a two-wheel system. Certain manufacturers provide airflows in both Scfm and Cfm. The energy calculations are based upon mass flow, so it's based upon if you were to go put a gauge on the unit in your location, you'd be getting what you would expect from that. So it really depends on a manufacturer to manufacturer in terms of what your what value they're providing with. But I'm assuming that most folks, if you're providing a rebate based on SCFM, would be able to give you that information accurately, regardless of whether or not it's actually in their report or not, or their sizing software. Okay, so will we obtain a webinar certificate? Yes, we'll send that out after the presentation's over. And one of the images, it shows a bypass around the energy recovery wheel. What are some reasons that you would bypass the energy recovery wheel? So if you are using bypass around an energy recovery wheel, it's typically to temper performance. So the reasons that I would think of being able to use a bypass is either to control the leaving air temperature, so the device is actually providing too much conditioning for you, and you have to tailor it back to deliver a certain specific leaving air temperature, or if you're using it in a climate where frost control is required. Now, I don't want to scare anyone with frost control. It doesn't come across stateside all that much, but it can be used to operate these devices in periods where frost may develop as well. Can you please go over the graph comparing outside air temperature and the EER, please? Yeah, I might use that. I might go through the other questions. I might tailor back to that question in a few seconds, just to see if I have any other pages I have to go back to. We get a lot of requests to design heating and cooling loads for wheel failure, which negate the benefits of being able to reduce the design loads. I will cite your extremely low failure rate to try to sway customers in the future. That's based upon Airxchange failure rates with our warranty 5-year period. But I personally work in this environment where I work with end users who have these devices installed, and I can say that there's a difference between perception and reality. So I think the perception is that these devices will break more than they actually do. Typically there's either maintenance-related items or there's service-related items. So the service-related items on, let's say, wheels are going to be motors and belts. I mean, there's no way getting around it. So kind of the average life expectancy for a motor and a belt is about 10 to 15 years. The average life expectancy that I see for wheels in the market, usually between 10 and 20 years. So the average age of when a project comes to me and says, "Hey, Chris, I got this old wheel, we need to replace it." Usually that wheel is about 15 years old at this point, or somewhere between 15 and 20. So they're pretty reliable, and they've gotten quite reliable in the past 10 to 20 years due to all the manufacturing increases that I've had, and then the tolerance is getting quite better. So please go ahead. In Seattle, is ERV or HRV recommended, and what goes into this decision? Boy, that's a loaded question right there. It really depends on the building, I will say, and what you're trying to accomplish in regards to the airflow delivery. Each building is going to be different. I will say that most designers that I see in Seattle kind of lean towards just sensible only design, but there are reasons that in certain applications, an ERV may be a better fit. Especially if you're trying to maintain a certain amount of humidity within a space. Maybe it's some sort of a process application or a space where you're trying to maintain an elevated level of humidity exchange. One of those things that kind of pops to mind is those hot yoga studios. Everyone's trying to keep the space at a very high relative humidity, but there's kind of benefits for both, and it's unfortunately going to be on a case-by-case basis. How do you add heat recovery to an existing HU, and can it be added? The biggest trick for adding or retrofitting an energy recovery device to an existing building is trying to aggregate all that exhaust air in a manner that it can be brought close to the incoming ventilation air. So sometimes this is, sometimes one unit's doing all that. Sometimes, if you look at most buildings that were designed in the 70s, you got the centralized intake and you got a ton of kind of exhaust fans that are scattered around the roof. But really, that exhaust air is really providing the regenerative aspect of the wheel. So that's going to provide you with all the work energy, all the thermodynamic energy that you need to do the exchange. So, if you can manage to aggregate that exhaust air and get it close, so that you can get the incoming ventilation air and the exhaust air side by side, then you can take advantage of it. Some buildings it's going to be a little bit easier than others. Sometimes it's going to take a little bit of crafty thinking, some out of the box thinking in order to do it. But it is accomplished. You can accomplish it. Is there any way to provide UV protection and disinfections in the ERU? So, we got asked this at the beginning of the pandemic period. I don't really see any benefit of having UV in the component compartment for an energy recovery device, because there is no standing water. And usually that air is being delivered downstream to what is being recirculated into the space. So it's usually being either delivered into the space or delivering it into a duct system that's going into a recirculated air system. And it's really the recirculated air system that probably benefit the most from a UV light. So you'd probably want to use it in its typical position, which would be in the coil compartment. But I don't really see any added benefit from adding UV to the energy recovery component device. And if you look at the leakage rates between an energy recovery device and a recirculation device, it's magnitudes lower. So the typical leakage rate of an energy recovery component, and this is both wheels and plates, is usually between 1% and 3% of total volume. And that's outside air volume. So that's not your total delivered air to the space. You're going to have a certain amount of recirculated air that goes into the space. So it's a small percentage of the smaller percentage of the air streams. The typical recirculated air going to the space is probably going to be what you're going to want to use the UV on. And once again, that's probably going to go into your typical space, which would be your coil section. Or upper air. That's also an option. All right, so they changed a replacement belt last week, and they sent me a link style belt, and it won't sit right. We do have videos on our website that kind of demonstrate how to do this. Usually when in my personal experience, if a belt's not kind of sitting right in the pulley, it usually means that the belt is off plane with the pulley. As these devices operate over the years, things can kind of shift a little bit. Perhaps the pulley shifted out and now it's getting pulled in a certain direction that can cause the belt to twist. But usually, or if you're putting a link style belt, so if you have a continuous link belt, if you're not careful to make sure that it doesn't twist, and if you somehow manage to get a twist in there, that could cause the belt to rotate. So you have to be very careful when you're using these interlocking link belts to make sure that the belt doesn't twist in the operation. The benefit of the interlocking link belt is they last a long time, so they work really good in that regard. But the true benefit is you don't have to pull the bearing, so you don't have to run the risk of maybe damaging the shaft or pulling the bearing, which is a considerably much larger project to do that. So once again, if you're having difficulties, please call us. We do have folks available to kind of walk you through the process, or go on our website and watch the video on how to do it, or maybe a combination of both. But we're here to help in that manner. How about noise considerations? So I do know, so our biggest way to market is through OEM sales. I do know, in terms of sound data, that's a big concern. The airflow that's going through an energy recovery wheel is laminar, so it doesn't create like an acoustical increase in noise. Especially not when compared to what it's right next to, which is the blower. So I don't believe any of our OEMs have ever expressed any any disadvantage from adding a wheel that would increase the noise of the wheel itself. But I could be wrong. But I don't really have a great answer for that. But I don't think it's going to add, especially considering once it's sitting right next to it, it's sitting right next to the blower, which is obviously going to be magnitudes louder than what the wheel is doing at 40 RPM. Okay. I think that's it for the questions. One person did ask me to kind of go back to the slide. So unless someone has another question, I think I'll just go back to that one. So what slide was that? I think it was the EER slide. Outside temperature EER slide. Okay, so let me see if I can get back to that slide for you so we can take another quick peek at it. Now, once again, you are dealing with the tolerances of the sensor here. But this is a kind of pretty average week here in the summertime. We operate usually, it gets pretty cool here at night. We're close to the water, so it kind of cools us down a little bit, and then it gets kind of hot during the day. But as you can kind of see here, if you're monitoring just the work that the rooftop is doing versus the over the power consumed, for the majority of the week, the rooftop unit's punching above its weight class basically. The unit was operated at 12 BTUs per watt hour, and you can see at the peak there we were getting about 17.8 BTUs per watt hour. Now on that day, this is just dry bulb temperature that you're looking at here. So on those days where you're probably getting 17.8, those higher those higher workloads out of it, it was probably a higher humidity day. So there really isn't a whole lot of temperature range in the summertime. Really, what adds a lot of energy load or energy consumed to a building is trying to remove all that water vapor from the air. So on days like that, those are probably what's causing those performance characteristics to go up so high, is because the component is now actively removing a tremendous amount of water vapor for you. So hopefully this, kind of what you're looking for. And it's just one example. You could probably use something very similar on multiple different climate zones. I'll just kind of leave that up there. Is there any other questions that I can answer while I'm here? Can you provide the source for wheel? It's based upon our internal warranty data. I don't think we're at liberty to actually give out those numbers, but that's based upon the warranty parts that we ship out as compared to, well, we monitor in parts per million, but parts per million converted to a percentage. But then that's based on things that we manufacture, so it doesn't include the motor on the wheel itself. But for the most part, these devices are reliable. They want to spin, and if you have a good maintenance regime in place, and like I said, maintenance regime, I think is kind of a double-edged sword. A lot of people think I have to do a ton of maintenance to these things in order to keep them operating, which isn't the case. It isn't the case at all. But I like to say proactive monitoring of these devices. So a little bit of legwork in terms of making sure that they're remaining clean and they're spinning and everything else is in order will go a long way enhancing the life expectancy of these devices, which in my experience is usually between 15 and 20 years is where we typically see these devices starting to reach their end of life expectancy. All right. Well, I don't see any more questions here, but don't feel free to email me after the presentation. I'll be happy to have a question, especially if you have a specific need or for a specific application. Once again, thank you very much. I appreciate you all chiming in here or coming in here today to listen in, and hope you have a wonderful day. And please keep an eye out for our next webinar invitation. Thank you.